electrical systems exist in a closed loop between the power source and the actual device being powered. To demonstrate this, what I've done is I've taken a piece of household Romex, which is exactly what you see. This is 14 gauge. This is what you would see in the walls inside your home. And what I've done is I've attached it directly to a light. So all it does is you have the hot coming in on this black wire, goes through the light, and then the return path comes here on the white neutral wire. You can see it lights up, but you can tell that it'd be unpractical and dangerous to constantly just manipulate wires by yourself. There's dangerous voltages, there's dangerous currents in here. So to overcome that, what we use is a switch, like this guy. Now all we're going to do is we're going to put this in between and you'll see how it works. Here what I've done is I've added in the switch. Now you at home, don't do this. It's going to have dangerous voltage going through here, but I know what I'm doing and I'm going to handle this safely. All I'm going to do is I'm going to plug it in and you'll see that the switch, all it simply does is it touches these two wires together and allows you to control safely this light here. So let's plug it in. You can see the light is on, which means we have continuity. These wires are physically touching on the inside of this switch. This touches this point, and then you turn it off, and it breaks. So all switch does is it makes by electrically touching, making continuous, and breaks the wire. To prove, furthermore, that all the switch does is touches these two metal pieces together, what I'm going to do is I'm going to plug this in, and all I have is right now is these bare copper exposed. So I'm just going to touch it just like that. And you'll see an issue with doing it that way. And it'll also prove the point that literally all the switch does is makes and breaks this electrical connection. So let's plug it in. Again, don't do this at home. It's dangerous. And all we're going to do is make and break the light. See? Made the light, broke the connection, make, break, make, break. Now, there's two issues I can see immediately doing it that way, right? One, obviously, that's super dangerous to just manhandle wires like that. You need a way to safely do it. This switch allows you to be electrically isolated while also controlling the contact points right there. But the other issue you may not think about is every time you do this, it actually sparks. The more power you have on your end-line device, the bigger the spark, there's heat generated, it can create an arc flash. So you need to make sure that when you're controlling it, that you, the user, are isolated from it. That's where switches come to play. But they are limited. They are limited by current. So this right here is a 15 amp switch, but I'll show you a 20 amp switch. Now here is a 20 amp four-way switch. Now, you don't really have to care about what a four-way does, but in this demonstration, what you should be concerned about is the size. So I might not be able to convey it perfectly on camera, but it takes a considerable amount of effort just to click this. Now it's easy enough for you to do because this is still relatively small of a device, but it takes a lot more force to move than this 15 amp switch. And that's because the conductors inside your 12 gauge wire, they are actually physically thicker in the cross section. So if you look at it this way, the wires are physically thicker to hold more current than its 15 amp rated 14 gauge predecessor. Why am I mentioning current? Well, you have to consider as the current in a system goes up, your ability to control it gets harder when you are the one manually operating it. The switches have to get bigger and bulkier in order to carry that current. It becomes more and more dangerous for you as a person to switch it. Now, that brings into play contactors and relays. So for really high current devices, you're not going to want to switch it by hand. You're going to want to switch it really fast. You're going to want to switch it autonomously. And that's where a contactor comes into play. Now this guy right here, I'm just looking at it, I can go up to 60 amps at 480 volts. Now if I were to do that same thing with a switch inside my house, there's two issues that come to play. You have 480 volts, I don't want my hand anywhere near that. And then you have the current aspect. I'm gonna need a massive switch that takes a lot of force in order to throw over. Whereas this contactor, it's really compact. I can remotely control it through its control wires. And all it does is it opens and closes. It makes or breaks, just like a switch, but this is an electromechanical switch. All it has is a coil, sucks in, and makes or breaks, just like a switch. Here's an issue with switches that maybe you didn't really think of, but almost everybody, I believe, has probably dealt with this problem. Now, if you want to add any sort of automation into a system, even something that's seemingly simple, like think about how do you automate your climate controls in your house? How does an HVAC system work? Well, you're not going up there with your thermometer and saying, let's say you want the house to be 65 degrees. You're not holding your thermometer and being like, okay, it's wintertime, I got to turn it on for 10 minutes exactly, and then go back downstairs, turn the switch off. That would be impractical and it wouldn't work. What happens when you're away? You know, you need a system that can automate and regulate based off of outside factors that isn't a switch, but it still acts as a switch. That's where relays and contactors become important, because I can automate the system and I don't have to think about it. It will act autonomously. Just do that switching action for us. Let's go take a closer look. Here we are at my thermostat, and all we're gonna do is we're gonna bump the temperature up. You should hear it click on in just a second. Did you hear that click? All that click does is it sends a control voltage, in my case it's 24 volts, out and down into my basement, and it turns on my furnace. Now that wouldn't be possible without a relay. Relays and contactors come in all sorts of different shapes and sizes. And really the only difference is a contactor is usually used to control more current, whereas a relay is usually for lower powered systems. Here are a few examples of relays and contactors that I found near me. This is actually inside an electric car charger. You can see that there are two wires on the left. That's the 240 volts, and on the right side of this contactor, it actually controls the voltage going out to the charger. And you obviously won't want to do that manually with a switch. Now these are relays that I found inside a radio control tower. This is automatically done, that's why we have the relays. And obviously, again, you wouldn't want to do that manually with a hand switch. Now this is an ice cube relay. This is one I found inside a elevator control cabinet, and then that actually controls a contactor shown here. This is a 480 volt contactor controlling the power going to a motor, which is in an elevator. And this last example is a contactor. It's a lighting control contactor. You can see here it's sucking in and going out. Now that you understand where we use relays and contactors and why they might be useful, let's talk about how they actually work. And the basic principle that they operate off of is electromagnetism. Here we can see an electromagnet that I made, and it looks awfully similar to exactly what you would see in a relay. All it simply is it's a coil of wire right here, but it looks kind of copper in color. But what you might notice is that it's slightly off color. It's because this coil of wire actually has a thin dipping of insulation on it. We just call that magnet wire. It's what you see inside motors, relays, and transformers. Anyways, it's just a coil of wire, and one end we attach the lead going to a battery, and the other end we add the other lead. So when we energize it, the coil of wire is energized and it creates an electromagnet. To demonstrate that, all I did is I took a bolt of ferrous, an iron bolt that goes through the center of that wire, and that directs the magnet. And you can see right now it's not energized. It doesn't pick up the metal. But as soon as I turn it on, I should be able to pick up. See? And now when I de-energize it, it'll drop it. I'll energize it again, pick it up, de-energize, drop. In this example here, this is actually a contactor. You can see there are 1, 2, 3 terminals on the top and 1, 2, 3 terminals on the bottom. And we have a coil here. Works just like the example we did before with our DIY electromagnet. The only difference is this one uses up to 120 volts. It's rated, you can see, 115 to 120. And what we're going to do is I'm going to take the leads of my power source, put one here, and you'll see how this actuates. This piece right here gets sucked in, and it does that electromagnetically. See how it's sucked in? It releases, sucked in, releases. Here's a closer look up at that automotive relay. You can see right on the case, it actually shows you the diagram of how the relay is wired. You can see that there's 2 sides of the coil, and then you can see how the contacts make and/or break. Now, that's not uncommon to be seen on all sorts of relays. Basically, every single one of those relays tells you how they are wired internally. Now, if we take a close look and pop it off, we can see a couple of things. Here, you can see it's simply a coil of wire here, which is the electromagnet. Now, that electromagnet is associated directly to pins on the bottom of the relay. Now, if we look on the case, you can see, maybe it might be hard for the camera to make out, there is a number 85 and a number 86. That is directly associated on the bottom. There's an 85 and an 86, and all we have to do is energize. When that coil is energized through 85 and 86, the actuator moves. There's a little contact there, and it moves in. Let's see if we can get this good on camera. It moves in like this. It's electromagnetically operated. So in the normal state, just like this, not energized, and then when it's energized, it sucks in. And now what that does is, you can see it's written right here on how it works. So normally between pin 30 and pin 78, you should have the normal state be continuous. Then when it's energized, 30 and 88 are then connected. Let's see if we can operate it. Here, all I'm doing is I'm taking a 14-volt power supply and I'm energizing the coil. So you can see that the armature is moving in and those 2 contact points are changing their state. Every time I energize, you can see clicking back and forth, and that is achieved really fast with automation. See how fast you can do it? It's kind of crazy. Let's take a closer look at a contactor. On the top of the contactor, you can see T1, 2, and 3. And then on the bottom of the contactor, you can see the points labeled L1, 2, and 3. All I've done here is I've taken my multimeter and I've connected from the top to the bottom. Now you can see, when you energize the coil, they become continuous. Now you should understand that relays and contactors are both electromagnetic switches. They operate on the same principle of electromagnetism. Now you should also understand at this point that they can come in many different form factors. In my right hand, I have a contactor, and in my left hand, I have a relay. You've seen many different examples of what they can look like. You should also understand that their control voltages are different. This relay that I have here operates at 12 volts DC. This contactor I have here operates at 120 volts AC. Relays and contactors provide a solution to how we switch things on and off. They also allow us to automate systems. Without them, we wouldn't have many luxuries of daily life. We wouldn't have automated assembly lines. We wouldn't have something as simple as running your car. There's relays that are in there. We wouldn't even have stuff like your HVAC system, which I showed earlier also uses relays. Hopefully you learned something today. I spent a lot more time on this video than I do on some of my other ones. I try to incorporate different shots, different angles for you, the viewer. Hopefully you understood, and hopefully this gave you a better understanding of how relays and contactors work and why we use them all the time, all over the place. Make sure you like, comment, and subscribe, and leave suggestions for any other videos you'd like to see. I think I have an idea for one coming up, which is going to be a hold-in circuit, which keeps into the theme of relays and contactors. But leave likes, leave comments. I want to know what your feedback is. And as always, thanks for watching.